An architect with a daring vision. A vision he will have to fight for. The Bahrain World Trade Center rises on the shores of the Persian Gulf. What makes this building unique is not its height or beauty, but its green technology. It will be the first skyscraper in the world to be powered, in part, by its own wind energy. In theory, it's a brilliant idea, but nothing like this has ever been attempted. With the Earth's temperature on the rise and the need for clean energy greater than ever before, the stakes for the Bahrain World Trade Center couldn't be higher. For decades, wind has led as the planet's #1 source of clean energy. Wind turbines worldwide have the capacity to produce 74,000 megawatts, which could power at least 20 million average US homes. Almost all this energy comes from big wind farms, usually located far from the people who use it. But now, one architect wants to bring wind turbines a lot closer to home. Right in the middle of a busy city, and right onto the very building they will power. The idea is the brainchild of a 37-year-old South African architect named Sean Keeler. Based in Dubai, Keeler has won fame for his skyscrapers all over the Middle East. But for 4 years, he's researched wind turbines, looking for a chance to use them in one of his buildings.
I've become very passionate about sustainable design and incorporating sustainable initiatives within projects that we are designing at the moment.
Buildings consume at least a third of the world's energy. Keeler wants to use green technologies like low-energy cooling systems and super-efficient glass that lets in light while rejecting heat. But he also wants to design a building that will create its own power. An avid sailor, Keeler knows how to read the wind. It is this skill that helps him sense the unique potential of the proposed Bahrain World Trade Center site.
In November 2003, when we first came to Bahrain, there was a tremendous wind blowing. My first impression is I should be sailing. I noticed the wind direction and the velocity of the wind.
Bahrain's capital, Al Manama, sits at the edge of the Persian Gulf. Each morning, as the sun heats the island of Bahrain, hot air rises. This creates an area of low pressure which draws cooler air in from the sea. This daily cycle produces strong onshore winds over 60% of the time. In the heart of the world's biggest oil-producing region, Sean Keeler finds the perfect location for a skyscraper powered by wind. During initial research, he faces the daunting task of figuring out where the wind turbines should go. Rather than just putting them on the roof, Keeler wants to incorporate the turbines into the building. He imagines them on bridges, between two towers stacked on top of each other. It's a great idea, but there are two major challenges. Turbine blades capture the energy of moving air, sending it to a generator which converts it to electricity. But to be able to rotate, the blades need uninterrupted winds coming directly at them. For this reason, wind turbines are mounted on vertical poles and can turn to face winds from different directions. Keeler's turbines, however, would be on a horizontal axis, fixed in position, unable to turn into the changing winds. The second major challenge is the way Keeler wants to stack the turbines. Because wind speed increases with height, the higher turbine will spin faster and create more power than the lower turbine. All three turbines need to rotate at the same speed, or the top one will wear out sooner. Keeler realizes the key to making the turbines work is the shape of the towers. Again, the architect's experience as a sailor provides the inspiration for the solution. The towers resemble two tall sails. In plan, they have an elliptical shape, like an aeroplane wing. To compensate for the turbine's inability to turn, Keeler hopes the shape and orientation of the towers will funnel the wind directly into the turbine's path. The tapering shape of the towers also means they will funnel more wind to the lower turbine and less wind to the higher one, making all three rotate at roughly the same speed, yielding approximately the same amount of power. It's a brilliant concept, but with no template to follow, the design poses a lot of unprecedented engineering challenges. Keeler needs time to find engineers who can figure out the technical details. However, less than a week after the architect presents the concept, a very enthusiastic client greenlights the project. Bulldozers are instructed to begin clearing the site immediately.
It was a fast-track job of enormous proportions.
With construction underway, Keeler begins searching for turbine manufacturers and bridge engineers. But very soon he discovers others do not share his vision or are daunted by the challenges.
Blade failure resulting in the machine toppling over is pretty rare. It doesn't happen very often at all, but it does happen. And if it were to happen in a situation where there's a bunch of people inside of a commercial building only a few inches away from the spinning blades, the possibility for people getting seriously hurt is very real.
Keeler emails dozens of turbine manufacturers and power providers. They all turn him down. 6 months pass and the Bahrain World Trade Center reaches the 5th floor.
During the research of all the turbine manufacturers that we were consulting, we found that a lot of them were saying, this can't be done. Turbines have always been placed on masts, in greenfield sites, not in an urban environment, and certainly not between two buildings, or on a bridge, where the dynamics of a turbine placed on a bridge compared to if they're on a pole are so different.
As the Bahrain World Trade Center grows skyward with each passing day, Keeler still hasn't found an engineering team to make his green vision a reality. Sean Keeler refuses to give up on his dream of the world's first wind-powered skyscraper. Finally, after 6 months, his persistence pays off. 4,500 kilometers away outside Copenhagen, 2 Danish companies respond to his pleas. Ole Sungil designs turbines. Lars Thorbeck engineers bridges. Normally their paths would never cross, but Sean Keeler wants to put a turbine on a bridge.
And a week later, I flew into Bahrain and I met Lars and Ole. And my first question was, is this really possible? And Lars looked at me and he said, yes, it is. It's taking 2 different pieces of ordinary engineering and just putting it together in a very special way.
So the bridge is stable, even at high wind?
Yeah.
The Danish engineers begin research immediately. They haven't got much time to prove to the world that Sean Keeler's daring vision can be realized.
Yeah, it looks very stable.
We have the weight on the backside. I think we should try to turn it just to see it in another direction. Don't you think so?
Yeah. I'll turn it to an angle where it's
First, they need to find out if the proposed wind turbines will produce enough energy to be worth their cost.
So you still expect it would be running at this angle where we are right now?
Yes, I do. Normally, when we have the wind turbine standing out in the field, the rotors will all the time turn in the direction of the wind, following the wind, and in this way create the maximum amount of energy.
But with turbines fixed in place on bridges, the engineers must calculate the wind flow between the towers.
Expect to just see the flow coming through here.
They set up a scale model of the building in a wind tunnel. Dry ice helps them visualize the wind flow patterns, and sensors measure the wind speed between the towers. The tests yield encouraging results.
It's a very nice flow pattern going through directly.
As the wind is forced through the gap between the towers, it accelerates 20%. But the engineers discover something even more surprising.
Yeah, you can easily see the shape of the flow coming through here and changing direction. We found out that when the wind hit the building, it kind of changed direction when you have a skew wind and make a kind of S shape going through.
The dry ice reveals the towers actually sculpting the airflow, taking winds and funneling them straight onto the blades. The engineers conclude that even winds coming from a 45-degree angle can still turn the blades. They estimate the turbine should be able to produce at least 15% of the building's energy needs. For Sean Keeler, the results are a pleasant surprise and a vindication of his design ideas.
I had some idea at that time that it would work, but I had no idea of how well it would work.
Ola Sangil now knows the turbines will receive a lot of wind. But this also means a lot of stress and fatigue on the materials, what engineers call load. Various locations around the world present different sets of wind patterns. So engineers must adapt a turbine to survive in local conditions. Ola receives 20 years' worth of wind data from Bahrain's airport and uses the information to calculate the winds that will hit the turbine over its lifetime. He simulates 199 wind scenarios, including a hurricane force blowing at 252 kilometers per hour. Ola determines how strong the turbine components need to be. Now he must find a manufacturer, but that might be a problem. The Bahrain World Trade Center requires only 3 generators and 3 sets of blades. For many companies, the order is simply too small. Another hurdle is size. The new trend in wind energy is megawatt blades. This is the largest blade in the world. At 61.5 meters, it dwarfs the 13-meter blades required for Bahrain. The LM glass fiber factory in eastern Denmark produces one of these huge blades every 2 days. A turbine with 3 of these blades will create 5 megawatts of energy a year, enough to power 1,500 homes.